Welcome back. So far we have had a conversation this afternoon talking about Nitro SSDs. We've talked about Graviton. And I think the next logical thing is to talk a little bit about our Inferentia and training, our machine learning chips here. So joining us now is Ron from our Inferentia team. Ron, why don't you introduce yourself?
Sure, yeah. So my name is Ron Diamant. I'm a senior principal engineer here at AWS. And I'm the chief architect for Inferentia and Trainium, which are purpose-built chips that we built from the ground up to accelerate inference and training workloads.
Awesome. So Ron, why don't we start at the beginning? So how did you get started with machine learning?
That's interesting. So my journey into machine learning probably started about 11 years ago. I heard of a group of super talented folks that are launching a new startup called Annapurna Labs. They had
I've heard of them.
Yeah. So they had a mission to modernize how we build chips. So I got intrigued, talked to the founders, joined the team, and we started building chips at a pace and quality that I've never experienced before. Back then, we were a small team building a new technology for data center workloads, and that eventually evolved into the Nitro system that you heard of today. Then in 2015, AWS acquired us. And since then, we've been tasked to provide more value to our customers running their workload on AWS. And one of the areas that we pay a lot of focus and attention on here at AWS is to accelerate and provide best-in-class infrastructure for customers running machine learning workloads. So that's what drew me into the field. And since then, in the last couple of years, I've been leading Inferentia and Trainium with the goal to do exactly that, to build the best possible technology to accelerate machine learning workloads.
So that's a really exciting journey you've been on since joining Annapurna Labs and coming over. With all the complexities that's happening, what do you think made you and Annapurna Labs start to decide on building machine learning chips here at AWS?
Yeah. So first of all, if we kind of zoom out, we see that machine learning is growing very rapidly over the last couple of years, and it's providing state-of-the-art results across a wide range of applications, spanning from personal assistants to recommendation systems, autonomous driving, and there are many more. But before we dive into the details, let's talk a little bit about what machine learning is.
Yeah.
So you can think of a machine learning model as a highly parameterized function, and then it has two phases, the training phase and the inference phase. During the training phase, we feed that function with a set of example inputs and corresponding outputs, and then we tune the parameters in order to learn the relation between the inputs and outputs. Then during the inference phase, we freeze the parameters, we don't change them anymore, and then we deploy the model, typically at scale, and feed it with new inputs to get the results from the model. Now, if we look at the last couple of years, we've seen that these state-of-the-art models are growing in size or in number of parameters very rapidly at a pace of about 10x per year.
And that growth is just due to the amount of data that's needed to make the models more accurate? Is that what we would attribute to? Or it's the accuracy of the outputs increasing as well?
Right. So it's both, actually. We grow the size of the model and the data set together, and once we grow them together, we get better accuracy. And one interesting thing is that the computational demand for training such a large model also grows at a similar pace of about 10x per year. But as we all know, compute servers aren't becoming 10x faster every single year. And that means that machine learning is becoming more complex. It requires scale out, meaning do a single training task on multiple servers, and correspondingly, it's becoming more expensive as well.
Right.
So seeing this trend, we decided to build Inferentia and Trainium and the corresponding AWS instances, Inf1 and TRN1, to enable our customers with AWS accelerated instances for machine learning that are fast, easy to use, scalable, and affordable.
So why don't we start with Inf1? So Inf1 is based on Inferentia, and it's tailored for inference, right? So, can you tell us about some of the benefits that Inferentia brings to customers?
Yeah. So what we did with Inferentia is to tailor it for inference workloads. And by doing that, we're able to cut costs and improve power efficiency. So here, for example, you can see that we benchmarked a neural network that is called YOLO V4. This is an object detection neural network, and it means that it identifies objects within an image and then bounds them with a box. You can see it in action on the right here. And in this benchmark, we measured power efficiency or performance per watt. So the higher, the better in this case. And we're comparing two platforms, the GPU-based G4DN instance and the Inferentia-based Inf1 instance. And as you can see, Inf1 provides between 1.5x and 3x better power efficiency. And what that means is that Inf1 instances are greener and cheaper to operate. And as always, we use that in order to pass cost savings to our customers.
And I can imagine that with this additional performance, the accuracy has improved as well, right? For the identification using a purpose-built chip.
So in this case, actually, accuracy remains the same because here we only deploy the model. This is the inference stage.
Okay.
But we can improve accuracy on the training side, and we'll get to train them a little later.
All right, I'm ahead of myself here. That's great.
All right, but I told you that we passed the cost savings to our customers, so let's talk about that.
Yeah.
So here we benchmark 4 different neural networks, and we compare 3 different instances here. G4DN and G5 are both GPU-based instances. Both are inference optimized. And Inf1, as we discussed before, is Inferentia-based and also inference optimized.
And here, lower is better.
Exactly. In this case, this is cost per inference, so we want a lower number. And as you can see, with Inf1, we can lower cost by up to 68%. So that's 3x lower cost per inference that you get by migrating to Inf1.
And maybe we should pause here and take just a timing note here. G4DN and G5 are pretty recent introductions in the GPU space, right? So that to me makes this reduction even more powerful, right? I mean, this is versus some of the most powerful GPU chips that we're offering in the cloud.
Right. G5 was introduced late last year,
right?
Way after Inf1, and still we see that Inf1 provides significant cost savings compared to it.
Right. So efficiency and cost savings are key here. That is what we're driving with Inf1, right? You talked about efficiency and also cost here.
Yeah.
Yeah.
Now we have quite a few customers that are already realizing the gains of Inferentia and Inf1. Internally, we have teams like Alexa, Amazon Advertising, Amazon Robotics, Prime Video, that are all running their workloads on Inf1. And externally as well, Airbnb, Autodesk, and Snap are all adopting Inf1 and seeing better performance and lower cost in their workloads.
That's amazing just to see the growth in the number of customers adopting Inferentia. Can we double click here and can you give us some specific examples of what our customers are using Inferentia for?
Yeah, so Prime Video, for example, moved from a GPU-based instance to Inf1, Inferentia-based instance, for their live event video analysis workload, and they saw a 4x speedup by doing this migration. And similarly, Airbnb migrated their support chatbot engine, and they saw an out-of-the-box 2x performance improvement, while at the same time reducing cost as well.
Wow, a 2x performance improvement out of the box just by switching to Inferentia.
Yep.
Right. Okay, that's pretty cool.
And then Abios is an interesting case. They're a data as a service esports company, and they were able to cut latencies and improve user experience by moving to Inferentia. And let's hear directly from them.
Abios is a data as a service esports company founded in early 2013 in Stockholm. Our mission is to facilitate the growth of the esports industry across the globe through our world-leading data and technology. At the core, we aggregate, normalize, enrich, and distribute data. To achieve this, we've been running a variety of deep learning models for text detection, text recognition, and object detection on GPU instances. Today, running this model pipeline on GPUs, we're able to process one 1080p image every half second on every live match. And as we cover several hundred matches every day, that ends up being a lot of inference. So any throughput improvement is extremely valuable to us, not only because we can reduce the amount of instances we're running, but also because we can reduce the delay between the video stream and our data, ultimately creating a better user experience for our customers. So having an instance type like AWS Inf1 featuring AWS Inferentia more catered toward inference throughput just sounded amazing. In initial benchmarking of our text detection model, we got especially excited when we found that we could reduce inference time by just straight porting our PyTorch models with a few lines of code. So now we're currently transitioning all of our text detection models and some of our object detection models onto AWS Inf1.
Wow, That's pretty impressive. And it's even better to hear a customer example. Here, there's nothing like seeing a customer example. And even cooler to see it using gaming as well. I have to admit, it's kind of a nice touch to also have him kind of display some of that gaming as well and see those performance improvements.
100% agree. I love seeing the customer success stories. Well, let's shift gears a little bit here. We talked a little bit about Inferentia. Let's switch gears and talk about Trainium now. Can you share some details about the Trainium chip?
Yeah, so Trainium is our second generation machine learning chip, and as the name suggests, it's optimized for training workloads. It powers two instances, TRN1 and TRN1N, and both of them deliver 3.4 petaflops of bfloat 16 performance and 13.1 terabyte per second of memory bandwidth. And with this capability, TRN1 delivers the best price performance for deep learning training in the cloud.
I never thought I would be talking about petaflops, excuse me, in here. But I think that goes to talk about our earlier comment is the amount of data that people are having to operate on in this machine learning space as well, the need for, the ability to deliver the 3.4 petabytes.
Petaflops, yeah. It's
Petaflops,
growing,
thank you.
Yeah, it's growing super rapidly, yeah. Now, one of the interesting things in Trainium is that it supports a rich set of data types. Now, let's explain why this is important. At the heart of it, machine learning computations are just massive linear algebra calculations. And these linear algebra calculations are typically done with floating points, and they can be represented with a set of different precisions. So one popular data type is float 32. That's a 32-bit representation of a floating point number. Recently, we've seen bfloat 16, a 16-bit floating point representation being quite popular. And we're even seeing a new trend with float 8, so a very compact representation, only 8 bits to represent a floating point number. And different neural networks have used different data types to achieve their optimal accuracy. And we even have some cases where we use mixed precision. That's where some of the computation is done with one data type and the other is done with a different data types. Now, the Trainium-based TRN1 instance enables our customers to choose the most optimal data type for their workload and supplies with significant performance benefits across data types, from 1.4x for bfloat 16 data type and all the way to 5x for float 32 data type relative to P4D, which is our fastest GPU-based instance.
Wow.
Now let's talk about another feature that is interesting and unique called stochastic rounding. So in Trainium, we baked into the device itself an ability to natively do what's called stochastic rounding. And to explain that, let's use integers as an example.
Yeah.
Most hardware platforms today support a rounding mode that is called round nearest even, or RNE for short. And that's very similar to the rounding that we learned how to do in school. So if I use integers, if I have 1.4 or anything below 1.5, it will get rounded down to 1. Anything beyond 1.5, above 1.5, will be rounded up to 2. Now, apparently, for machine learning workloads, that's actually not the best way to do rounding. There's a better way to do it, stochastic rounding, and let's try to get some intuition on why. Let's say with integers for now, let's say that we have a weight value of, let's say, value 1, and we want to update it with a small increment, 0.2. So we add 1 and 0.2, still in integers, so we'll do a rounding step, and after rounding, we'll get a result of 1. Now, even if I add 0.2 to 1 5 times in a row and do a rounding step after each addition, the result is still going to be 1. And here I think you can intuitively see that we're losing precision, that something is not ideal here. Because if I hadn't done the rounding steps, if I add 5 times 0.2 to 1, I should get a result of 2, not 1.
Right.
So stochastic rounding solves it by performing the rounding in a probabilistic way. So what happens here is that we take this value, 1.2, and then we round it according to the relative distance between the two closest representable values. So 1.2 will have 80% chance of being rounded to 1, and 20% chance of being rounded to 2. And over large computations, like we have in machine learning, this tends to average out and provide with more accurate results. What we've seen, by the way, is that for some network, we can speed up end-to-end training by up to 20% using this technique.
Yeah, I think this is a great example of how we've done continuous innovation across like the product lines that we've had, right? We've talked about the other products that we've talked about before too, but here especially as we talk about the introduction of Trainium, it's not just training models, it's also this unique kind of rounding that we're providing to improve the performance for customers, recognizing the amount of data and the complexity of training. So I think it's really cool technology that we're able to talk to here. And I didn't think we would spend some time getting some high school math lessons again.
That's awesome. Always up for learning. So for training, it's not just about the chip though, right? It's also about what we do at the server level. Can you talk a little bit about what we're doing at the TRN1 level?
Yeah, that's a great one. So we talked at the beginning of our conversation about needing to scale out, to do a single training task on multiple devices and sometimes multiple servers as well. And we built Trainium and TRN1 to enable efficient scale out from day one. So part of it is equipping the TRN1 servers with a high bandwidth, low latency interconnect between the training devices. We call this interconnect Neuron Link. Now this interconnect enables 768 gigabytes per second per device and at a 2 microsecond latency. So very high bandwidth, very low latency. And when you need to connect multiple servers together, we offer the Trainium Ultra Cluster, which connects more than 10,000 Trainium devices together in a single cluster with non-blocking petabit scale of EFA network that delivers up to 1.6 terabit per second of network bandwidth for a single TRN1N server.
It's just incredible performance, incredible scale.
Yeah.
Right.
Wow.
I mean, 10,000. These are really, these are large numbers, but the fact that we're able to do that, I think, is an artifact of working in the cloud as well. Our ability to scale to these large numbers. I think even we heard the statistic this morning from Dave Brown as well. Like 60 million instances are launched every day, 720 per second type thing. But joking aside about it, this talks to me where else are you able to kind of like get those number of clusters other than if you kind of expand in the cloud? I think that's one of the advantages of the offerings that we have in the cloud.
Yeah, absolutely.
Yeah, and it's not just about hardware, right? It's really about the marrying of the hardware with what we're doing on the software side. So can you talk a little bit about what we're doing in terms of the software and the SDKs?
Yeah, that's a great point. Actually, when we talk to customers, that's one of the first inputs that we tend to get, that customers appreciate a simple and flexible solution. They don't want to start optimizing their models for different platforms, but rather they want to come with their own model and be able to deploy it on any instance that they choose. So that was one of the key tenets that we used for Trainium from the very first day. We basically aim to enable customers with a just works experience. And for that, we built the AWS Neuron SDK, which supports all popular machine learning frameworks, like you see on the screen here. It has three major components to it: a compiler, a runtime, and a set of developer tools. And our goal here is to enable customers to come with their own model. They add a few lines of code to compile it seamlessly and run it on our target hardware, whether it's Inferentia or Trainium. And we don't require any operator tweaking, model changes, data type conversion. Just bring your model and we'll run it.
And this is the same Neuron SDK that's used for Inferentia as well, as you pointed out. So now what customers can do is really do end-to-end training and inference using the same SDK.
Right, exactly right, yes. And we're extending Neuron over time to enable our customers with more capabilities. So especially as we launch Trainium and we start providing with customers more experimentation methods to build new models on the Trainium platform, we introduced Eager Mode, which enables customers to work very interactively with the hardware with a very fast compilations to try new things out as they build a new model. As we talked, we need to support scale-out, so we support a couple of distributed training libraries. And there are a couple of other new features, including dynamic shapes, custom operators. And of course, we integrate all of this with AWS services like SageMaker, EKS, ECS, and others.
So it really sounds like essentially what we're also doing is trying to make this as simple as possible. When you're bringing your existing model over, you have to just make a couple of code changes, do a recompile, you can start using this. So it's kind of creating a total ecosystem that allows someone to easily adopt the Trainium and Inferentia instances.
Exactly, and that's actually quite important for us. We spend a lot of time in making the transition as simple as possible because we think that's the way that customers want to interact with the new infrastructure.
Yeah, I feel like that's also a hallmark of the effort of the combining software and hardware that we've done at AWS. And it's also something that we've done and that Annapurna Labs has also done when we talked about the Graviton programs and other programs, the simplicity of being able to get started with those programs. So it's really cool to see that here as well, Ron.
So let me show it to you.
All right, oh, even better.
So here I want to run through an example of training a model called BERT Large. And BERT is a natural language processing model that achieved state-of-the-art results across a couple of different applications in the last 3-4 years. It's an interesting model. You actually probably used it, even if you're not coming from the machine learning space, because one of the main benefits that we get from BERT, or one of the main applications that we use it for, is what's called similarity retrieval, and that's just a fancy name for web search. So here you see code, a training script code built on top of the PyTorch machine learning framework. And what we do here is we download the BERT Large model from the open source Transformers library by Hugging Face. And then we're going to add just a few lines of code and compile it to Trainium. So I want to emphasize this point. Nothing here is unique for Trainium. We didn't build the model for Trainium or optimize it, but rather we download the model, and then I'll show you a couple of lines of code here that make the model be just in time compiled to Trainium, and then we are able to run it on the device.
Wow.
Now, a training run for this size of a model typically takes multiple hours or even more than a day, so we don't have time for that. But
I'm grateful you're speeding this up for us.
But I'm speeding this up quite a lot. And we're seeing 3 graphs on the screen here. On the left, we have the loss. And the loss is a value that we try to minimize during training, and it has an inverse relation to the accuracy of the model. And as you can see, it converges to a value of somewhere about 1.4 here. And then in the middle, we have throughput, which is just as it sounds, how many sequences or sentences per second we can process with this during training. And on the right, we have the gradient norm, which is just a debug tool that we use to see that training is converging. Now, this first run is extremely conservative. Let me explain what I mean by that. Before I talked to you about the different data types that machine learning practitioners choose between in order to trade off between performance and accuracy. So in this run, we went with a full floating point 32 model with only the matrix multiplies being done in bfloat16. So this run is going to be slower than the maximum performance that we can achieve with a smaller and more compact data type. So now let's change to a very aggressive run. Let's optimize for performance. So we're going to change everything to bfloat16 with the default rounding mode, round nearest even. Now, when I say everything, I truly mean everything. And for the machine learning practitioners in the crowd, I mean the optimizer state as well, and I mean the master copy of the weights as well. So everything is bfloat16, and let's see how it behaves. So first thing that you see is that throughput improved a lot. And we expected that because we moved from a floating point 32 data type to bfloat16. But another thing that we see here is that the loss value doesn't get to the same 1.4 as before, which means we lost accuracy. This is actually not a new phenomena. Machine learning practitioners are aware of that, and that was why I gave the comment before.
Yeah.
And typically, the way that they solve it is via mixed precision. That's where some of the variables or tensors during training are kept in floating point 32, specifically the master copy of the weights and the gradient, and the optimizer, apologies. Now, we can do better than that. There's actually a downside of keeping some of the model in floating point 32, because that means that the memory footprint is quite high. And as we scale up to very large models, that large memory footprint becomes a problem. Either we need more machines in order to fit the model, or we cannot fit a larger batch size. So let's see what we can do. This is the same exact aggressive run. Everything is bfloat16, but this time we turn a switch and use stochastic rounding. So let's see what happens. So throughput is just as good as before, and we expected that because Trainium natively supports stochastic rounding. But look at the accuracy. In this case, accuracy almost exactly matches floating point 32, which means that we truly got the best of both worlds, the performance of bfloat 16 and the accuracy of floating point 32.
This is really impressive. We talked before about how stochastic rounding, the kind of how it is an innovation, but just to see it in an example in action here kind of also highlights the benefits of that to customers. And also, as you mentioned, this kind of essentially has cost and performance impacts for customers in training these models.
Yeah, absolutely. We saw up to 20% for some models.
Wow,
Incredible.
that's really nice.
That's it. That's how we built TRN1. We built it to be the most cost-efficient deep learning training platform in the cloud, and we're super excited to see what our customers do with it.
So Ron, we had covered quite a bit today in such a short time. Is there anything that customers should know that we have not covered?
There's a ton, but one thing that we didn't cover in a lot of depth is the float 8 data type, which is quite a promising data type, especially for large models where the memory capacity and the memory footprint becomes quite critical. And with float 8, we actually made it a configurable float 8, which means that customers get to choose on a per operator basis how the bit layout is used. So how many bits we use for exponents, dynamic range, and how many bits we use for mantissa or precision. And there's quite a lot of papers out there that show that you can use that in order to converge faster during training.
Awesome.
So I think that customers can start right now working and using Inferentia, and we have a preview running as well for Trainium, so folks can take a look and get started right now.